So because we've had such enjoyment working with the fundamental theorem of calculus, I'm proud to say that there is a second part of the fundamental theorem. And different textbooks call it different things. Here we'll call it the second FTC, sort of a part 2. So the first part, again, is how we find the exact value of a definite integral. And I have that listed right here at Roman numeral number 1. But part 2 says that the second FTC provides us with a way to find the derivative of an integral defined function. So that if my function is defined as an integral from a to x, then the derivative would basically be found by taking my upper bound and just placing it in to the variable that you see in the integrand. So that's the second FTC. What I'd like to do in this video is walk through a couple examples with you and then end with sort of more of like an FRQ style question here where it says number 3, 3 parts A, B, and C. So we'll do these first two. Number 1, find the derivative of f of x. F of x is defined as this integral function. So f prime, according to the second fundamental theorem of calculus, would simply be the square root of x plus 5. That's it. It's deceptively simple. F prime is just the square root of x plus 5. Let's try number 2. Take the upper bound, find the derivative by taking the upper bound, and we're going to substitute that inside of the integral itself here. So f prime of x in this problem is going to be cosine of x cubed minus 2. Now I've got to be careful because the upper bound is a function, and I want to apply the chain rule here, so I'll multiply by the derivative of the upper bound. In this case, that would be multiplied by negative sign. So once again, that's all there is to it. If the upper bound is a function, don't forget that chain rule piece to apply it to the derivative value. There's no plus c. We're not writing antiderivatives. We're actually writing normal derivatives. So f prime is negative sine of x times cosine cubed minus 2. Now let's tackle this FRQ. There's a function down here, and that function is the graph of f. The graph of f. So I'll label my vertical axis here, f of t. Letter A says to find h of 1. So just like I would do with any function evaluating problem here, I'm going to just take 1 and plug that in for x. So h of 1 would be the integral from 1 up to 1 of f of t. And there's really not much work to do because if I'm evaluating the definite integral from 1 to 1, then I have no area. The bounds are the same. There's no area there. So h of 1 equals 0. How about letter B, use the graph to find h prime of 1. H prime of 1. Show the computations, and notice this, that the graph is linear with a quarter circle in there as well. We'll come back to that in a little bit. Well, the graph of h prime of 1, let's not worry about h prime of 1 until we first have established what the definition is of h prime of x. And for that, I'll need a little bit more space. So let me just come down here, and I'll write down my integral again. I'll just recopy it. H of x is defined from 1 to 2x minus 1 of f of t. But I want now h prime of 1. So let's find h prime of x. H prime of x. I'll plug in my upper bound and for the function right there. So f of 2x minus 1. Chain rule times 2. Here's my definition of h prime. And the problem said to find h prime of 1. So h prime of 1 will be f of 2 times 1 is 2 minus 1. So f of 1 times 2. And f of 1 for my picture here appears to be negative 2. So I have negative 2 times 2, or negative 4. So h prime of 1 is equal to negative 4. I had to apply the second fundamental theorem of calculus to find the derivative of h defined by that integral function. Finally, part C, use your answer from part B, and then the graph to find h double prime of 1. Find h double prime of 1. So now I want the derivative of a derivative. Well, if h prime of x is defined as f of 2x minus 1 times 2, that was from before. In fact, I might actually put the 2 out in front right here. So I found that from my previous step. Let's find the derivative of that. So h double prime, well, that would be 2 times f prime of 2x minus 1 times the derivative of the inside, which is another 2. So that's a chain rule piece. Let's simplify. I'll have 2 times 2, or 4 times f prime of 2x minus 1. And I'm looking for h double prime of 1. So now that I have this reasonably simplified, let's plug in that 1 and see what we have. So 4 times f prime of, again, 2 times 1 is 2, 2 minus 1 is 1. Now where's f prime of 1? I have to be careful here. F prime of 1 is the slope of f, the derivative of f. Here's my picture of f. And at 1, I'm looking at the slope of this line right here. It is piecewise linear, and that slope appears to be, if I compute it, looks like the rise is 2 and the run is 1. So a slope of positive 2 means that my derivative value at 1 is positive 2. So 4 times a slope of positive 2. There's my solution. H double prime of 1 is equal to 8. So the second FTC is a way to find the derivative of an integral defined function, and I like number 3, just sort of a series of parts that you might see on a calculus FRQ. That's what the second fundamental theorem of calculus is all about.